Thank you for submitting this great talk, Rainer, and I'm looking forward to seeing and learning about the 40 years of evolution, how to go from functions to coroutines.
Thanks, Jens. So let me continue. To be honest, it's about the evolution of functions, but also of the different flavors of different kinds of functions we have. And only to give you a mindset, have a look here. This is just a function template, which takes something callable and invokes it using the two additional arguments A and B. And depending on the C++ standard, you can do it in various ways. For example, you can use a function. This means in C++ 98, you use this function add1, two arguments 90, 100, and 98, and you get, of course, 90, 100, 98. What you can also do in C++ 98 is using a function object. A function object is a special class having the call operator overloaded, and it looks like this. You instantiate the function template, and then you use it. With C++ 11, you can use a function. You can use a lambda. In this case, it's a type-based lambda. It's a typed lambda, to be more precise. 3 years later, you can use a generic lambda. You could also say auto is a so-called unconstrained placeholder. With C++ 20, with the upcoming C++ standard, you can use a constrained placeholder, meaning a concept. So you see, there's a lot of evolution going on, but this is only part of the story. So let me start. I start, of course, with function. Then I go to function overloading, come to function objects, then special function objects, or essentially these are function objects. I talk about lambda expressions, and at the end, of course, I talk about coroutines. Let me start with functions. I make it quite short because I assume you know what functions are. Okay, it's a sequence of instructions that performs a specific task packaged as a unit, of course. Implementation, a function call creates a stack frame. Okay. The stack frame contains the private data, parameter, locals, and return address. And at the end of the function, the stack frame is deleted. Sounds similar, but I have to add something. What we call functions in programming are not functions in the mathematical sense. What does this mean? A mathematical function has a well-defined semantic. It means, so to put it another way around, a mathematical function is a so-called pure function. What's a pure function? A function which always produces the same result when given the same arguments. This is formally called referential transparency. Such a function could not have a side effect, so it could not change or depend on something which is outside the function body. And of course, this function does not change the state of the program. For example, square is a pure function. But of course, a function such as time, random, or a function having or using state outside the function or doing some kind of input-output could never be pure, because the function execution depends on the state of the program. What are the benefits of pure functions? First of all, they are easy to test. Why? When square of 2 gives you today this result, it will give you tomorrow the same result. And because you can reason about this function in isolation, they are easy to refactor. Think about how would you test a function like time? What is the expected value? I don't know. It goes on because the result of the function invocation does not depend when you call the function. You could reorder the functions. You could even execute the function on a different thread. And which is nice when you know that square of 2 will always return the same result. You can cache the result from the previous run, and with the next run, you just return the old value. So pure functions are quite comfortable. Okay, well, we don't have pure functions in C++, but based on discipline, we can do them, or we can implement them. For example, you can use a comment function that's such as this power function. This power function here is pure because it does not affect anything outside its function body. When you execute a function during compile time, such as a so-called meta function, this function is also pure. Here's a meta function which also calculates m to the power of n. When you execute this function, say you want to calculate 2 to the power of 10, you resolve this call by saying 2 to the power of m is the same as 2 to the power of n minus 1. And this part goes to 0 or to 1. And now you need a boundary condition. And this is this partial specialization in case n is equal to 0. So by definition, m to the power of 0 is 1. So this function can calculate m to the power of n at compile time, and at compile time there is no state. And by the way, this is the reason why template metaprogramming is called, in C++, is called a pure functional language embedded in the imperative language C++. Okay, but we have more. With C++ 14, I mean the C++ 14 syntax of constexpr, we can declare a function as constexpr, which gives the function the power to run at compile time. Now the function is pure when it runs at compile time. And one step further, you see here, I mentioned the first time C++ 20, which C++ 20, you can declare it as const_eval. This means this function always runs at compile time. This function here, to make the difference, could run at compile time or runtime. It runs at compile time when it's used in a so-called constant expression. Okay, but this function cannot run at runtime. It has to run at compile time. And here are the various invocations of the functions. The comment function, the meta function, the constexpr function, and the const_eval function. Okay, this was it about functions. Now want to go one step further and talk about function overloading. Okay, what is function overloading? You can create multiple functions having the same name but different parameters. And now it's the job of the compiler to find the best fitting function. Okay. And how does the compiler achieve that? Quite easily. It mangles the name. What does it mean? When you call print int, for example, the GCC puts the int as an e inside of the function name. This is the GCC 8.2 syntax, and this is the Microsoft syntax. You see, e is kind of replaced with h, and here double with n, here with d, and this is a const char pointer. And when you want to learn more about name mangling, you have to look here, and you see each compiler, in even compiler version, has a different syntax of mangling the names. You see, this is what it described. This is all GCC. Anyway, You see, this is what I described, GCC 3.x. Okay. So essentially, there's only one function, and the compiler uses this function, the parameters, to invoke the right function. And I said the compiler uses the best fitting function. These rules are quite complicated. So here's only a short glimpse at it. What does best fitting function means? For function, it means a function fits better if it needs fewer and less costlier conversions. Okay, this function is preferred by the compiler. For function and function template, it means that functions are preferred when they are as good fit as function templates. I will show you an example in the next slide. For function template specialization, it means the more specialized function would be preferred, and for concepts, similarly, the more constrained function template would be preferred. If you want to know the full truth, this truth is quite long. You see the rules to overload resolution. Have a look here. How long it goes. Of course, I will not tell you the truth. So this picture should help you to get the essential information. Okay, now I want to show you two examples, one about function template, one about concepts. Here I have function overloading. You see, I have a function and a function template. Both have the same name, only double. And now the question is, what would happen if I invoke only double with a double? When I invoke only double with a double, I have two possible candidates, this one and this one. The generic or the function template is always an ideal fit because it's generic. But here, double is also an ideal fit. This means in this case, the double function would be preferred. Or the function taking double would be preferred. But when I use a floating point value, this is an ideal fit, but this not, because a floating point has to be expanded to a double. And this is kind of work which the compiler don't want to do, so it prefers the function template. In this case, I would get an error because I deleted this function template. This means this construct allows you to say, I only want to have a double without implicit conversions. So all implicit conversions are suppressed because the function template would kick in. Okay, now to something new. Let's go to concepts. Okay. By the way, this is a concept: forward iterator, bidirectional iterator, and random access iterator. Okay. Let's start.